Oh, good morning. Don't forget to sign in the chat. And yeah, I'm supposed to be given a key to a classroom here on campus, so I'm having to work from my office space. And so I'm going to have to use my camera rather than um, uh, the school setup. And because of that, because I'm using my camera and I have to go through the network here, um, I've been having troubles with connectivity. In my 10 o'clock class, my Zoom kind of fritzed out on me. And what I was showing everybody kind of froze up. And so I had to exit the Zoom and come back in. And fortunately, I could do it and not lose the Zoom meeting. So, yeah, which is what I was afraid of, that if I exited, because nothing showed up. A bunch of pictures showed up. Some of the Zoom videos showed up from the students, but what I was showing froze. My shared screen froze, and so I had to hit the X in the window, not leave the meeting, but because that didn't show up, nothing would show up. I'd roll my mouse over the Zoom picture and nothing happened. It didn't show the menu bar across the bottom. It didn't show anything. And so I hit the X in the upper right hand corner and nothing happened. And so I went and re-entered the Zoom meeting, and it magically changed back to the way it was supposed to. So that fixed it. So hopefully things will go better this class period. I won't have to do that. And we are at time. Oh, we're a minute into it. So let me go ahead and, any questions about anything? There are some issues with people who still haven't gotten in with the temporary. They are in with a temporary, but haven't gotten their access code. Please realize that the access code is I've sent out a lot of the access codes, or most. I think everybody's. There's only one or two people who haven't gotten any, and they're not in this class. So whatever your email is that you used when you signed into MyLab, that's where I sent the access code to, that email address. So if it's your school email you use, then go to your ACES email. If you used a personal email, then go to that personal email and look for the code that I sent. All right, let's get this up and running. Does anybody remember what slide we were on or what we were talking about when class ended? No one's saying anything. No one's writing anything. Nope.
Unfortunately, I can't recall.
Okay, were we talking about did we do the piecewise functions?
We were on the rate of change on the slope.
We were about to talk about the secant line.
Yes.
Okay. That's great help. Well, where is that? It's after that. Here we are. Finally found the spot in the PowerPoint where we're at. Okay, let me go back to the Zoom. Please be sure you are signed in to Zoom for attendance purposes. And hopefully I won't be writing up here. Okay. So the slope, what we had been talking about was well, it's not doing it. Why isn't it doing it? Here we go. Finding the average rate of change between lines, between points, is finding the slope of the line that connects those 2 points, which is what we're talking about here with the secant line. The average rate of change of a function from A to B equals the slope of the secant line containing those 2 points on its graph. So that's what the thing is talking about. So finding the average rate of change of this equation. So you have f of x equals x squared minus 3x plus 2. And you want to find out what the slope average rate of change of g is from 1 to 3. So you're going to set x equal to 1 and then do g of, oh, it's a g function, not an f. You're going to do g of 1, and then you want to know what happens when x is 3. So you're going to do g of 3, I usually find out what these are first, and then I just put them into the formula. I already know my denominator is going to be 3 minus 1. My numerator is going to be g of 3 minus g of 1. So g of 1 is 1 squared minus 3 times 1 plus 2. So I get 1 minus 3 plus 2, which is 0. And then g of 3 is going to be 3 squared minus 3 times 3 plus 2, which equals 9 minus 9 plus 2, which is 2. So my numerator is g of 3, 2, minus g of 1, which is 0. So 2 minus 0, which is 2, divided by 3 minus 1, which is 2. So that's just 1. So the slope of my secant line is 1. And I have 2 points. I have the point 3, 2, right? 3, 2, and the point 1, 0, right? 1 gave me 0, 3 gave me 2. So those are my 2 points. I'm going to use the point 1, 0 because those are easy numbers to use, right? And I traditionally use y equals mx plus b to find the equation of the line. Okay, I'm sorry, I'm having to fix something over here in this other slide. I mean, this other screen I have up. And chat window. Okay. So the slope we got was 1, so that's what m gets replaced with. So this is y equals 1x plus b. I have a point. I'm going to use, I actually have 2 points, but I'm going to use this point, 1, 0. The y value is 0. The x value is 1. And what do I add to 1 to get 0? Well, negative 1. So subtracting 1 from both sides gives me negative 1. And so this here now becomes y equals 1x minus 1, because the plus b gets replaced with the minus 1. And this is the equation of the line we're looking for. Oh yeah, and this part C here is just looking at where they what do they look like when you graph them. So okay. Yeah. So the average rate of change, they did it same way I did. Okay. And so the slope is 1. And now they're going to use a point slope. So the slope they got is 1. But they choose one of these 2 points. It doesn't matter which one they choose. They happen to choose the same point I did, because 1 and 0 are easy numbers to use. So they're going to put 0 in for y sub 1 and put 1 in for x sub 1. Okay. And then they end up getting the exact same equation. Right, they got the same equation I got over here. So they could have done the same thing using 3, 2. So it would have been y minus 2 equals x minus 3. And so you get y minus 2 equals the x minus 3. Adding 2 to both sides, you get y equals x minus 1 because you're adding 2. Negative 3 plus 2 is a negative 1. So again, you get the same thing. If I had done that, if I'd used 3, 2, then that would have been 2 in for the y equals the x value 3 plus b. Subtracting 3 from both sides, you get a minus 1 equals b. I get the same b value I got over here. So it works out the same way. It doesn't matter which point you use, and it doesn't matter which form of the equation you use, either point slope or slope intercept. Either way, you wind up getting the same equation. And we always want to solve for y because our function is in that form, f of x equals y equals. Okay, so we always want it as y equals because that puts us in the function notation form. Now, we're going to talk about the library of functions. They go through a lot of explanation here. Which is a little helpful when you're doing transformations and such. But we'll get to that when we get to it. All right, graph the functions listed. All right, we're going to have the graph of the functions listed in the library of functions. Oh, wait a second. Sorry about this. Okay. Just had to add my workspace so I can. So this part is time. Well, let's just move into it. And then the second part is what a piecewise function is and how to deal with it, basically. So here we have x, the square root of x. Okay. So f of x equals the square root of x. That's what this is supposed to be up here. This part here is supposed to be this right here. I had corrected it on some of the PowerPoints, but since they updated the PowerPoint, I didn't. Well, yeah, since they updated the PowerPoints, I don't necessarily have them here corrected. So the domain and range is a set of all non-negative real numbers. So that means anything that isn't negative, that's 0 on up. If you were to write it in integral notation, it would be from 0 to infinity, closed at 0, open at infinity. And in set builder notation, it would be the set of all x such that x is greater than or equal to 0. And for the range, they'd use y instead of x. And the range would look exactly like this. The x-intercept is putting, setting the function equal to 0, and you get You get 0 is the x value that gives you 0. And when you put 0 in for x, you get 0. And so 0 is both the x-intercept and the y-intercept. So the point 0, 0 is the x and y-intercept. It contains both the x and y-intercept. The graph is neither even nor odd, and it's an increasing function over its domain. Okay, see, here's the domain, and it looks just like this interval, and so it's increasing. That means it's a one-to-one function, but we'll discuss that later. And it has an absolute minimum at 0, at x equal to 0. So the graph of this thing at 0, it's 0, at 1, it's 1, at 2, 3, 4, at 4, it's 2, and at 5, 6, 7, 8, and at 9, it's 3. And so the graph of it looks something like this. And yeah, so, and that's a closed dot, not an open dot. I don't know if you can see, but the tip of this pen is not. I need to replace it, the tip of this pen. So, and those are all that they're in my desk at home. So that's why I wasn't drawing the line exactly where I wanted it to go, because that point is really weirded out on me. Okay. Next thing. Now they're switching gears and they jump to f of x equals the cube root of x. And so even or odd. So that means we're going to do f of negative x. The cube root of negative x, f of negative x is the cube root of negative x, which happens to equal the negative of the cube root of x. So cube root is that when you take the cube root of a number, it's going to be positive or negative. It's going to be negative if you're taking the cube root of a negative number, and it's going to be positive if you're going to take the cube root of a positive number. So when you change the sign of x, you're changing the sign of the cube root, which means this is the negative of the f of x, which means it's odd. Okay. Now to find the x-intercept, to find the y-intercept, you put 0 in for x, so the cube root of 0 is 0. And to find the x-intercept, you set the cube root of x equal to 0. Well, that means x has to be 0. So here you get the point 0, 0, and here you get the point 0, 0. So again, the point 0, 0 contains both the x and y intercepts. Okay, and I missed this part. Back when we determined it was odd, that means it's going to be symmetric with respect to the origin. And now the graph. For years I've been dealing with this graph, and I've been dealing with whole numbers rather than fractions because it's fractions and nobody likes fractions. I like them. I think they're fine, but most of my students don't. And so I'm going to use 1/8, and I'm using numbers that I know the cube root of. I know the cube root of 8, so the cube root of 1/8 is the cube root of 8, the reciprocal. Okay. Sounds like a Broadway play. Okay. and then 1, and then 8. And because it's an odd function, whatever numbers I get here, these ordered pairs, I just change their signs, and that'll give me the y, the mirror image through the origin. And so the cube root of 0 is 0. The cube root of 1/8 is 1/2, or 1/2. Excuse me. The cube root of 1 is 1. The cube root of 8 is 2, because 2 times 2 times 2 is 8. So it takes 3 2's being multiplied to get 8. That's the definition of cube root. So I'm going to graph those points to begin with. Whoops. Let me go this way a little bit further because it's 8 I'm dealing with. So here we have 0, and here we have 1/8, and here we have 1, 2, 5, 6, 7, 8. So 0, 0, and then 1/8, 1/2, 1/8, 1/2, and then 1, 1, and then 8, 2. So the graph on this side of 0 goes like this. And then because it's an odd function, I negate the 1, 1, so that's -1, -1. I negate the 1/8, 1/2, so that's a -1/8, -1/2, which is about here. And then 8, 2 becomes -8. 2, 3, 4, 5, 6, 7, -8, -2. So I mirror this graph over here. And there I have it. Ba-doom. So they determined it was odd and was symmetric with respect to the origin. They found the x-intercept and the y-intercepts. Okay. And then we use a table to find using positive values for x, knowing full well that if I negate both the x and y, that'll give me the mirror images. And so there we have it. So what I used to do is instead of using 1/8, I'd use 0, 1, 8, 27, because the cube root of 27 is 3. So, but I couldn't get 27 on this graph or any graphs I usually used unless I changed the scale to accommodate it, and then these points down here get lost. But anyway. So the next thing, here are the properties of the cube root function. The domain and range are all real numbers. So if you're looking at the graph here, you can tell that it's all real numbers, both in the x direction and in the y direction. It's going to cover all the real numbers. The x-intercept, y-intercepts are both 0. It's an odd function. It's symmetric with respect to the origin, which we used to graph it. And the function is increasing over its domain. Its domain is all real numbers. So it's always increasing. As x increases, the y is increasing. And it does not have any local minima or maxima. So it doesn't have any local extrema, nor does it have any absolute extrema. Kaboom. Now they're going to start talking about absolute value. So is it even or odd? So we do f of negative x, which is the absolute value of negative x, which equals the absolute value of -1 times x. That way I can deal with the negative sign separate from the x. And so when you have taking the absolute value of a product, then you can take the absolute value of each of the factors and multiply them. So the absolute value of -1 times x is the same as the absolute value of -1 times the absolute value of x. So that just gives me the absolute value of x, which is f of x. So I just came full circle. I came back to f of x up here. All right. So that means it's even. And that means it is symmetric with respect to the y-axis. Okay. So it's symmetric with respect to the y-axis. And we can use that fact to help when we graph it down here on letter C. The intercepts are quite easy. You put 0 in for x and you get 0. So that's the y-intercept. I always find the y-intercept first because it's usually easier. And now I set the absolute value of x equal to 0, and that tells me that x is 0. And so that's the x-intercept. So like on the previous problem, the point 0, 0 contains both the x-intercept and the y-intercept. And then to graph it, I'm gonna do the same thing I did previously. I have my x. And my y, only I think they add the process column in the middle. And since it's an even function, I'm going to do 0, 1, 2, and 3. And whatever I get for the y values are going to be the same for the -1, -2, -3. So I just change my signs on my x's, and that gets the appropriate mirror image. So the absolute value is 0, 0, absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3. So I'm just going to graph those 4 points. At 0, we're 0, at 1, we're 1, and at 2, we're at 2, and at 3, we're at 3. So this is the right-hand side of the graph. Now the mirror image, I changed the sign of my x. Well, 0 stays 0, so that didn't move. But changing the x value 1 to -1, that brings us over to here. Changing this x value negative brings us over here. And changing this x value negative brings us over here. And so now we have this graph, the left side of the graph, the left arm. And we'd be done with the graphing. All right, here they're talking about how can we get it to be even. They do the same thing I did, only they didn't show this middle part in here. The x-intercepts and the y-intercepts both equal 0, so this point 0, 0 contains both the x and y-intercept. And then using a table, they use the same 3 numbers I did. Excuse me, sorry about that. Guess I should get more sleep. There we have that. So it's the same way I did. Now, the properties of the absolute value function, the domain is all real numbers, and the range, we look here, the range starts here and goes up. So although the domain is going to be all real numbers, the range is only part of that, because it starts at 0 and goes to positive infinity. So it's closed at one end and open at the other. And it starts here and goes up. So that's why they did the set builder notation, and I included this here. Because sometimes in MyLab, when they ask for these things, they'll either ask for as in set builder notation, or they'll ask for it in interval notation. So I like to give both, just in case MyLab might ask for both, or they'll just ask for one. And they're never consistent on which one they ask for if they only ask for one. So on one problem, it might ask for the interval notation, but if you work the problem again, they may ask for the set builder notation. So I just like to have y'all be able to write it either way. The x-intercept of the graph is 0, and the y-intercept is also, is 0, yeah, and the y-intercept is also 0. The function is even, so it's symmetric with respect to the y-axis. And the function is decreasing up till you get to 0, and then the function is going down, and then once you get on the other side of 0, now the function is going up. The y values are increasing. I don't know. No, I don't think I discussed it with y'all. Heard me talk about this on Thursday. After my 8 o'clock class, I happened to run into the dean of my school for mathematics and some other subject areas in the hallway, and he's a mathematician. And I asked him about this, about how, I said, when you're talking about where a function is increasing and decreasing, from my understanding, you use they're open intervals. And he goes, yeah, that's right. And I said, well, the author of the textbook says no, it's closed intervals. And he looked at me like I was nuts. And I said, well, he uses, if it's an interval between two real numbers, they'll use the brackets and say that it's a closed interval. And he said, that's wrong. And I said, that's what I thought. And so he's wrong. Mr. Sullivan is wrong. He's been an author of mathematics textbooks for 10, 20, maybe 30 years now, and has authored hundreds of books, not just this book, but and he's using the wrong notation here. So fucking all right. I got it done. I knew I was right. All right, so here are some of the key functions. All right, so we have the constant function. This is just a horizontal line. It's an even function. You can even see that it's even because it's symmetric with respect to the y-axis. All real numbers is the domain, and its range is a single number. The y values neither increase nor decrease, hence it's a constant. And so its domain is that y value. The range is that y value. Let me think. Oh, okay. It's constant over its entire domain, hence the name constant function. And there's some other things. I can't remember them right now. And then we have the identity function, y equals x. Okay. It goes through the point 0, 0. It's an odd function. That means it's symmetric with respect to the y-axis. I mean, we're symmetric with respect to the origin. It is increasing over its entire domain. What else? It has its x-intercept is 0 and its y-intercept is 0. There's some other things that are true about it. Here's the square root, the square function, x squared. It's we've used this as an example of even functions ever since we started talking about these things. Well, so the domain is all real numbers. The range is y greater than or equal to 0. And it's decreasing from negative infinity to 0 and increasing from 0 to positive infinity, just like the absolute value function does. Here we have the cube function. It's another odd function. F of negative x equals negative of f of x. So the f of negative x equals the negative of x cubed. We have the square root function, which we already discussed. It's neither even nor odd. The cube root function, which is an odd function, has all those properties. And then we have the reciprocal function. The reciprocal function is an odd function. All right, because if I do negative x, then that's going to be 1 over negative x, which is the negative of 1 over x, which is the negative of f of x. Okay? So that makes it an odd function, which means it's symmetric with respect to the 0, to the origin, but the origin is not part of the graph. As a matter of fact, this graph has no intercepts, either x-intercepts or y-intercepts. It's decreasing from negative infinity to 0, and it's decreasing over its entire domain. So it's decreasing over the interval negative infinity to 0, and decreasing over the interval from 0 to positive infinity. So this is a decreasing function over its domain, which means it has a reciprocal function. It has an inverse function. And we'll discuss that. Later. And then the absolute value function, which we discussed earlier. The greatest integer function, which is a funky little function, it has x-intercepts. The x-intercepts from 0 to 1, but it's closed at 0 and opened at 1, because it can equal this endpoint, but it won't equal this endpoint on the x-axis. Notice that this forms like a staircase, and these are sometimes referred to as step functions. I almost always refer to them as step functions. The greatest integer function, it's the greatest integer less than or equal to x. So at -1, -1 is equal to -1, and that's the smallest. That's the greatest integer that's smaller than or equal to. Now, when you go to -1/2, the largest integer that's less than -1/2 is -1. So from -1 up to 0, all the y values are going to be -1 until we get to 0. Then we jump up to the number 0. And it's going to be 0 until we get up to 1. And once we get to 1, it jumps up to 1. And so for the numbers from 1 to 2, not including 2, all the y values are going to be 1 until you get to 2. Once you get to 2, it jumps up to 2. So it takes a step up. And it stays at 2 until we hit 3, and then it takes a step up to 3. And it stays at 3 until we get to x equal to 4, and then it steps up to 4. And the y values stay at 4 until the x values get to 5, and then it steps up to 5. And it keeps on doing that forever because the domain is all real numbers. Yeah, there's gaps at the integer values, but they're included in the next portion of the graph. So all the x values are included. But the y values are just the integers. The domain is the integers. So the domain, the range would be all y such that y is an integer. Because you only get integers back. You can put any real number in, whether it's an irrational number or a rational number, a whole number or a negative whole number, you're going to get integers back. So the integers are the y values. That's interesting. Okay. Now we're going to start talking about piecewise. Okay. Piecewise functions are called piecewise because the domain has been broken into pieces. So here my domain has been divided into 2 pieces. And the 2 pieces, I like to look at them on a number line. So I have my dividing point. I have my endpoints for the here it's divided into 2 pieces. And each of the 2 pieces have an endpoint. And that endpoint is the same x value. Okay. But it's not included in the low end on this side of this, but it is included on the other side, on the larger x values. It's included in that portion of the domain. So the domain comes from -infinity and comes up to 2. And then, but once it hits 2, it jumps over to the other function, but there's no discontinuity between the x values, even though there is going to be one in the graph, and it continues on to infinity. So the domain is all real numbers. That's an important thing to understand. Okay, so there we go, find the domain. But when we're in this part of the domain, which is less than 1, we're using the equation 2/3. We're using the expression 2/3 x plus 1 for the function. And when x is equal to 1 or bigger, then we're going to use the equation, the expression x minus 2 plus 1 for the function. So when I do f of 0, well, f of 0 is on this side of 1. So I'm going to use the 2/3 of x plus 1. So 2/3 of 0 plus 1, which is a 0 plus 1, which is 1. And then when f is 1, well, f is 1 is that dividing point. It's the boundary point, but it's included in this interval. It's included in this interval here. So that means I'm going to use that equation. A negative 2x plus 1, I'm using that expression. So it's going to be a negative 2 times 0 plus 1, which is 0 plus 1, which is 1. And now we're asking for f of 2. Well, 2, again, is in this interval, right? So that means we're using this expression. And so it's going to be a negative 2 times 2 plus 1.
Sir, for the f of 1, you put 0 for the x instead of 1.
Whoa. Thank you. So that means that's going to be a negative 1. So this is the point 0, 1, and this is the point 1, negative 1. Thank you. And here we get a negative 4 plus 1, which is a negative 3. So that's the point 2, negative 3. The reason I did this is because they asked us to graph. And so here I have some points that I can use to graph. Locate any any intercepts. So the y-intercept is easy to find because that's putting 0 in for x, which is this in using this domain, which we already found. So the x-intercept is at the point 0. No, the y-intercept, sorry, is at the point 0, 1. The x-intercepts is setting the function equal to 0. Now, we have to use all the functions here, because when I want to know if x less than 1 gives us an x-intercept. So I'm going to use 2/3 x plus 1, and I'm going to set that equal to 0. And then I'm going to look at the other portion of the domain where x is greater than or equal to 1. And so I'm going to set that part of the function, the negative 2x plus 1, and I'm going to set that equal to 0. And I'm going to see if the x values I get here fit the criteria here, fit the domain for that particular function, or that particular portion of the function. So I'm going to subtract 1 from both sides. So I have 2/3 x equals a negative 1. I'm going to multiply both sides by the reciprocal, 3/2. So I get 1x here equals 3/2 times negative 1, which is a negative 3/2. So is negative 3/2 in this domain? Well, yeah, negative 3/2 is down here. So it is here. So negative 3/2 is an x-intercept. Now we're going to look to see, do I get an x-intercept for this in this portion of the domain? Knowing that we can have multiple x-intercepts. I just need to find out if this one has multiples. Okay, so now I'm going to subtract 1 from both sides. So negative 2x equals a negative 1. Dividing both sides by negative 2, I get x equals 1/2. Right, dividing by negative 2 changes my signs. Now, negative 1/2 is not in that domain. Negative 1/2 is down here. I mean, positive 1/2 is down here. So it's not in this portion of the domain. So I can't use it. Can't use that. It's extraneous. So we just have 2 intercepts. The 2 intercepts is negative 3/2 0, or negative 1 1/2 0. When graphing, I used mixed numbers because they're easier to graph than the improper fraction. And then the y-intercept is 0, 1. So that's what I can do when I start graphing. I can start using those things. So I have 1, 0. And I have a -3 half 0. And I have the point 2, -3. Now we need to start finding out what other points are. Oh, no, we have the point 1, -1. Whoops. This was 2, -3. And then 1, -1, which is here. Now, 1 being a boundary point in our domain is very important. I need to look to see what each portion of the graph looks like at that boundary point. Even though 1 is not part of the domain of this function here, of this portion, I want to know what's going to happen. What is happening to the function as x gets closer and closer to 1 from the negative side? What's happening to the y values? Well, so I put 1 into that function. I do 2/3 times 1 plus 1. And I know it's not going to equal that point, so I'm going to use an open dot for that point. So I'm doing this, I get 2/3 plus 1, which is 1 2/3. So when x is 1, the y value is 1 2/3. So I'm going to put an open dot there at 1 2/3. And the graph of this line is going to look like this on that side. On the other side, it drops down here and goes down this way. I could put 3 in to this. So 2 times -2 times 3 is -6. -6 plus 1 is a -5. So at 3, it goes down to 1, 2, 3, 4, 5. This point here, I kind of hit it. Not really, but okay. And from the graph, we can determine the range. Okay. So here we have a highest y. We don't have a lowest y value. So that means it's going to be coming up from -infinity. But we do have a highest y value. Now it comes up to, but does not include this y value, this y value. So that's, and I'm going to write this as 5/3. 1 times 3 plus 2 is the numerator, divide by 3. So it's going to come up to 5/3. And since it won't equal that y value, we use parentheses there. So this is the range. Questions? I kind of zoomed through this, but all right. And so now they're going to go through and talk about this stuff. First, we must identify which occasion will be used in the evaluation. And so depending upon where x is, tells us which one to use. And so 0 gave us 1, and 1 gave us -1, and 2 gave us -3. And that was this portion here. After somebody pointed out that I put a 0 here instead of 1, corrected my work. And then the domain of the first equation is the function of the function is a set of all real numbers less 1, and the set of the second equation includes 1 and goes up. So it includes all real numbers. The y-intercept is setting it equal to x equal to 0, and you use the appropriate function for that. So they went and set the first one equal to 0 and got -3/2. And they set the second one equal to 0 and got +1/2. And the result 1/2 is disregarded because it does not satisfy the condition for that interval. And so a -3/2 is the only x-intercept that this function has. And so that was this part here. Oh man, I did it again. I did that last class too. I hit, instead of hitting my right arrow, I hit the N button on my keyboard. And so that put me way down. That's the very last slide of this set of this PowerPoint. So now I have to scroll all the way back up to find out where we were. We're not there yet. Oh, there we are. Functions. And graph of functions. And properties of functions. Is that where we're at? No, we're at piecewise. There we are, piecewise. There we go. Now, to graph this, look at the graph I did, and hopefully you copied it down, did it too. And look at their graph. What's wrong with their graph? Because their graph is wrong.
It connects.
Yeah, it connects them. And it has this portion not going that way. They have it going down this way, which it does not happen. So when they talk about the range, they write down the wrong range because they graphed it incorrectly. So yeah, they screwed up. Okay. So now here we have another piecewise function. So again, the first thing I always do, I look at my graph, where the function is defined. It's defined starting at -4 and goes up to, this is 0, and it goes up to +2. And so when x is between -4 and +2, including 4 but not 2, we're going to use x plus 2. So in this interval, we use f of x equals x plus 2. Now, when x is 2, then we use f of x equals 2. So that means f of 2 equals 2. That's the point 2, 2. Now, once we get on the other side of 2, going up this way, we use another function, f of x equals x squared divided by 3. So 2 is a boundary point. It's not included in the lower in the lower domain, lower portion of the domain, it's not included in the upper portion domain. It is the middle domain. Now, just looking, and I'm doing letter B first because it's real easy to see on this graph. Although there is kind of a hole here at 2, it's been plugged up because we defined the function when x is 2. So that means that it's going to start at -4 and it's going to go to infinity. And it can include 2. Another way of writing this in set builder notation, it's all x such that x is greater than or equal to 4. So the domain doesn't take into account that we have breaks in our function, because the x values are still going to be covered. All of the x values are going to be covered from -4 to infinity, including -4. Okay, now I go back and I look at letter A. I want to find f of 0. Well, here's 0, and 0 is in this part of the domain. So that means I'm going to do 0 plus 2. So that's the point 0, 2. And again, since they're graphing, that's why I'm writing these ordered pairs, so I can use those in graphing the function. Now, 2 is its own domain, right? F of 2. Well, we already said f of 2 equals 2. So that's the point 2, 2. What we already discussed here when we discussed that portion of the domain is a single value. Right now, 3 is in this portion of the domain. So we're going to use this function here. So my f of 3 is going to be 3 squared divided by 3, which is 9/3, which is 3. So when I put 3 in for x, I get 3 out for y. Now comes the fun part of locating intercepts. I have 3 domains. So I set each function for each of those domains equal to 0. So I have x plus 2 equal to 0. And for if I get an x value here, it has to be between -4 and 2. And then the next one is 2 equals 0, because that's the function. The function is 2. And so 2 equals 0, and that's for when x equals 2. And then when x is greater than 2, we use this function, x squared divide by 3. So I'm going to set x squared divide by 3 equal to 0. I find the x values that work, and then I look to see, are they in this domain? Do they fit this criteria for the domain? And so here I'm going to subtract 2 from both sides and get x equals -2. -2 is in this domain, right? -2 is here. So we would use that function. So the point -2, 0 is an x-intercept. So we have one of them so far. 2 equals 0, well, that's a false statement. And we have no solution. So we don't get an x-intercept from this part of the domain. This part of the domain, we get x squared equals 0, because multiplying both sides by 3, this just becomes 1x squared, and this 0 stays 0, and the square root of 0 is 0, so x equals 0. But 0 is not greater than 2, so this does not give us an x-intercept. because 0 is not in part of this domain. So now I have a bunch of points I can graph for different parts of the function. And so I'm gonna come over here. All right. I have the point -2, 0. I have the point 0, 2. So those are my two intercepts, and they are both in this portion of the, and then because -4 is an endpoint of this interval, okay, we got those intervals from -4 to 2. And then we have this other interval from 2 to infinity. So I want to check these two endpoints as for these two functions, as well as knowing that at 2 we have a specific y value, which is 2. So at 2, y is 2. All right. But I need to find out where it is at -4. So I put -4 in there. So -4 plus 2 is a -2. So at -4, we have the point -2. And it includes that point. So at -4, I go down to -2. Now this portion of the graph comes up right like this. But it continues on the other side of 0 as well, up to 2, but it won't include that point. So I need to look and see what happens at +2 as well. So I'm going to do 2 plus 2, which equals 4. So I wrote a 0. God knows why. So the point 2, 4 is part of the graph, is an endpoint, but it's not part of the graph. So the way I show that it's an endpoint, but not part of the graph, is by putting a 0 at the point 2, 4. And I continue on connecting them. So for this part of the domain, this is the graph. For this part of the domain, at x equal to 2, this domain, this is the graph. I know I have a point at 3, 3, which is here, and it's part of this domain. So it's part of that function. So again, like we checked 2 in this portion, even though it's not part of it, it is at the endpoint. We want to check this endpoint for this graph. So I'm going to put 2 in for x squared over 3. So I'm going to get 2 squared over 3, which equals 4/3, which is 1 1/3. And the reason I write it as a fraction, because that's easier to graph than the mixed number is easier to graph than the improper fraction. So at 2, I'm going to go up to 1 1/3, and it's going to be an open dot. Let me put a little more distance there between the two. Okay. And so it's going to go up like this. If I put, and I would do this simply for my own, because I like to see what's actually happening there. So I'm going to put 3 in for x. So that's going to be 3 squared divided by 3. Oh, we already did that. 4 squared divided by 3. So that's 16/3, which is 5 1/3. So I go up 1, 2, 3, 4, 5 and 1/3. And so, okay, it's going like that. I was going in the wrong direction a little bit there. So it's that portion of a parabola. Now, looking at the range, we have a lowest y value. The lowest y value is at -2. And the y values start at -2 and go up forever because we have a little bit of overlap here, but it covers all those y values. So it goes from y equals -2 to y to infinity. So from -2 to infinity. Now, it can include -2. It does include -2, so I put a bracket at that end. Or we can use it in set builder notation since we're talking about the y values. It's going to be the set of all y values, all real numbers y such that y is greater than or equal to -2. And so here we go through their explanation of the thing. And so putting 0 in for x, and then putting 2 in for x, and then putting 3 in for x is using the appropriate function for that particular portion of the domain. And continue on through. And so that's what we did up here with this right here. This was A. And then they're asking for the domain. That's kind of what I did up here with the domain. That was B. And I did that first because from my point of view, it's easier. It's just easier to do it that way. I don't know. So they give us the interval notation. They give us the set notation. They say set notation. I say set builder. Means the same thing. Set, when you're using set notation or set builder notation, you're using the braces and stating a specific condition or conditions. All right, so letter C, what was letter C? Letter C was finding the intercepts. All right, we already found the y-intercept by putting 0 in for x, and then setting each portion of the domain, we use those three functions to determine, do we have an x-intercept in that portion of the domain? So we check out for that portion, and we get that x is 2. And for the second portion, we get that there's no solution. And then for the third portion, we get that it's 0, but 0 is not in that domain. Let me see. And so, did they even talk about it here? But 0 isn't in this domain. They didn't talk about that. Oh, and the second potential. Okay. Okay. They didn't even discuss this one because there's no X in here to find a solution to, so they didn't even talk about it. Okay. And so they came up with the two intercepts. This intercept and this intercept. And we look at the, and to graph it, we looked at the portions in different portions of the domain, and so they graph them appropriately. And I was happy to see that they graphed it correctly. Okay. Any questions here? Oh, and then the from the graph, you can see that y greater than or equal to -2 for this particular interval is the range. In most cases in mathematics, we're not too concerned about what the range is. We are concerned about where maximum and minimum values are. Relative maxes, relative mins, absolute maxes, absolute mins. But I don't know. All right, so here we have a situation that calls for a piecewise function, because our domain is split up into two different ways of looking at the function. So we have and we're going to be using X for the kilowatt hours. So when our kilowatt hours is less than or equal to 700, we use one formula. And when X is greater than or equal to 700, we use another formula. And so those are our two things to look at. What is our cost function going to be? Well, it's a piecewise function. So we're going to find out what those two functions are. So what is the charge for using 500 kilowatts per hour? Well, for 500 kilowatts, which is less than 700, so we use this portion of the graph.
Quick question.
Yes.
Seeing as it's only over the 700, would that still be equal to or greater than or equal to, or just greater than?
Just strictly greater than. Oh, thank you. I knew what I meant. Okay. As he says in a whiny voice. Okay, so the cost of 500 means it's going to be $20 plus, and I'm going to rewrite this 11.48 cents as dollars. So that's $0.1148 times the number of kilowatt hours. So that's going to be times the 500. So this is solving A. And I'm going to let them solve it for me, or if someone's got a calculator handy, you can do it real quick. And letter B, they want to know for 1900. So the kilowatt hours for 1900 well, 1900 is more than the 700. So for the first 700, they're going to be doing this. They're going to be doing 20 plus the 1.1148 times the 700 plus the remainder. And the remainder is going to be 0.1160 times what's left over, which is 1200. For the first 700, this is what you get charged. And then above the 700, this is what you get charged. Is that making sense?
Yes, it makes sense.
And so you just plug it into the calculator. And this gives us $77.40. Round to the, you only round until once you're done. Okay. Keep all the decimals until you're done. Till you get your final answer. Yes, that's my final answer. Okay. And then for 1900, the charge is the this is making no sense. Okay, so all right, so a dollar. All right, so yeah, so $1.40. I mean 0.00 for the first 700, plus $1.60 for the, I mean 11 cents 60 for the kilowatt hours in excess of the 700. So yeah, they came up with the same formula, which is $239.56. And I'm pretty sure these didn't come out to exact pennies, and you just round appropriately. Now that X represents the number of kilowatt hours used. So for the first 700, we're going to use the 1148 times X plus the 20 plus the $20. So that's going to be the 0.1148 X plus 20 when the number of kilowatt hours is less than or equal to 700. Now, once it's above 700, we're going to do this, do the 148, I mean the 0.1148 times 700, because that's for the first 700, plus 20 plus the rate, the new rate, the 0.1160 on the number of kilowatt hours over 700. So this gives us over 700. This gives us 700 because it's over 700. So we have to, we're charging this at a different rate than this. And so you do this, we can simplify. And so what we wind up with is 0.1160x plus 19 something. I can't remember what it is right now. And so that's what they do. Well, yeah, they put it, yeah, because the number of kilowatt hours, you can't use negative numbers of kilowatt hours for this formula. If you're doing solar or wind power and you're selling some of it back, well, that's a totally different. They don't buy it at the same rate they sell it. They buy it back at a much cheaper rate than what they sell it at. Okay. And so that's what I have here. Okay, let me write this a little better up here. From 0 to 700. No. And then they're going to do the same thing down here. Okay, so for the first 700, this is what their charge is going to be right here. And then for everything over 700, this is what the charge is going to be. And then they use, and then they simplify the equation. Okay. Use the distributive property here. And, oh, 16. I thought it was 16, but I couldn't remember. $19.16. So the rate over 700, we just multiply it by the new rate and add $19.16 for it. So your basically what happens, the slope of the line changes, your rate of change changes, as well as your x-intercept. So although the smallest amount of money you have to pay every month is still going to be $20, even though that's not reflected here, because this formula already assumes you're using more than none. Okay, and so there you have it, those two functions, which is what I wrote up here. Okay. So this graph is a little off, right? Because what they're saying here is, if you notice, the slopes are going to be different. The slope of these two portions of the line, when x is 700, these two formulas give you the same dollar amount. So at 700, it doesn't matter if you use the less than or equal to, or if you use the greater than 700, you're going to get $100.36 as the cost of 700 kilowatt hours. Please note the two pieces are linear, but they have different slopes and meet at the same point. Now, this portion should have a steeper slope than this portion does. But from my point of view, every time I look at this, it looks like this has a shallower, although very slightly shallower slope than this part of the line. But just could be how I'm looking at it. I don't know. I actually should graph it in my own graphing calculator and see what's going on there, but I'm not going to do that now. Okay. So graphing techniques, transformations. We're going to get into transformations here in a little bit. We're going to talk about vertical and horizontal shifts. We're going to talk about compressions and stretches, and we're going to talk about reflections, either across the x-axis or the y-axis. Very quickly. Vertical and horizontal shifts. I'm either moving the graph up, or I'm moving the graph down, or I'm moving it to the left, or I'm moving it to the right. So the graph is going to look exactly the same, except I'm just moving it where it is on the graph. So I could move it up and to the right, or down and to the left, or down and to the right, or up and to the left. So the shifts, it's going to be the same shape. If it's a parabola I'm moving, it's still going to be a parabola. I'm just going to move it to a different place. Now with compressions and stretches, a compression, it's like you're stepping on it and you're making it flatter, or you're squashing it towards the x-axis. So a compression in the y direction is you're bringing it towards the x-axis, either from above or below. That's what a compression is in a horizontal, a vertical compression. And you have vertical stretches. Well, that's going the other way. That's pulling it away from the x-axis. So it's like a spring. You're going to pull it out, or you're going to compress it down. And so that happens same in the horizontal. A compression is moving it towards the y-axis, where a stretch is pulling it away from the y-axis. A vertical compression looks like a horizontal stretch. They're not the same. They don't line up the same way, but they look the same. It's just what's happening kind of looks like it. It looks like the other. And a vertical stretch kind of looks like a horizontal compression. So there's not symmetry, but it looks like it. And then reflections, well, that's just like when we talk about that functions that are symmetric with respect to the y-axis, that's just flipping it across here. So you're just changing the sign on the x. And then when we're talking about to the y-axis, here we go. This is my pointer here. To the y-axis, to the x-axis, then that's just flipping it from up here to down here, or down here to up here. So you're changing the sign, your y. You're changing the sign on your y's. When you're reflecting across the x-axis, you're changing the sign on your y's, because you're going from up here to down here, or you're going from down here to up here. So it all depends upon how you're looking at it. And then when you're reflecting across the y-axis, then you're changing your x value. So this x goes to this x, but the y value stays the same. And same thing here with that one. So boom. Okay. And we'll start with this next time, talking about a vertical shift up. I don't like the functions they ask us to use. Well, x squared is a nice one, but there are others that would be easier to use, is all I'm saying. So I'm going to stop sharing now because I feel selfish. All right. Any questions? Please be sure your name is in the chat over there. And unless you have questions for me, I'm going to say bye-bye, and you can go away.
You have good
Just
dinner.
come back. Just come back Wednesday. Okay. I see y'all. Somebody want to talk? Have questions? I mean, nope, no questions. Pedro, you got questions, or are you gonna disappear on me too? Okay, well, I'm gonna disappear us both then.